I was unwilling to discuss with you something about spherical capacitors yesterday that should be brought up. And this isn't on your test, but I've neglected this a little bit this year. The fact that there are interesting things out there beyond the curriculum. And this is something that's in our curriculum and is interesting, but may not feel like it has to do with what you think it has to do with, the way we've done other things for capacitors. So I want you to consider a parallel plate capacitor. I'm sorry, not a spherical capacitor. We did this problem yesterday, and it is, I can skip through parts of it. By the way, I don't, all right, back to this. We got to a point where we had an expression for the electric field, and this is, obvious, so I'm not going to spend a lot of time. And we used that to figure out the electric potential by taking the integral of our expression for the electric field. And we did that from A to B. And that's how we kind of structured this question. And we said that the outer surface was negative Q and the inner surface was positive Q. I want to make sure I have my train of thought ready to go. You still get a valid, verified capacitance if you set your outer shell at infinity. Meaning, what if the outer shell was located a distance infinity away? When you run this, you will get all the way to the end in the same place we did, Q over 4 pi epsilon naught, and you have negative 1 over R evaluated from A to infinity. Now, yeah, you can make that a plus and switch your limits. And then when you plug in your values, you get, 1 over A minus 1 over infinity, which this goes to 0. What this leaves you with is Q over 4 pi epsilon naught A as the electric potential, because we ran the outer plate to infinity. So this is what we would have gotten for the electric potential if we had done the whole calculation from electric field and went from a place where there is 0 electric field all the way towards the edge. That's why this looks like the expression we have for electric potential, because we set the other plate at infinity. But then plugging it in for our expression for capacitance gives us 4 pi epsilon naught A as our value for capacitance. This is a valid capacitance, which means any spherical shell acts like a capacitor with only one plate. Now, what's the usefulness of this? If I charge up a shell, how do I get that energy out? Sometimes capacitors are created by accident, meaning it's plausible that you can have something that is a capacitor and not know it's a capacitor. Right now, if you crumple up a sheet of aluminum foil and turn it into a ball, it is suddenly a capacitor and can store charge and discharge that stored energy. We may not see that as a particularly useful capacitance. In fact, if you try to run this with any value for A that's in a real-world size, you'll find that capacitance is very, very, very small. However, it's not very small when you think of bigger things. The Earth is a capacitor. It stores energy as it moves through space, collects charged particles from the sun, and can discharge that energy sometimes to passing objects like spacecraft and space stations. We have as much discharge of electrical energy to the ground from lightning as we do into space from stored capacitance of the Earth. And all planets act as capacitors in space because of this. They're all spherical, one-sided capacitors and store electrical potential energy. It's a little interesting, maybe in an academic sense, but it also means if you're trying to land your spacecraft, you better be careful on reentry. or you will discharge the capacitor through you if you are at a lower potential when you enter. Now, most spacecraft and things that are coming from someplace else to the Earth are not that far away. So they never really leave the planet. But coming back from the moon was far enough away to be where the electrical discharge against spacecraft was going to be measurable. When they landed on the moon, they reset zero potential for the moon, and then had to come back to the Earth. So it's a real thing. I'm not sure I could explain much more about what its potential is, and I shouldn't have used that word, what its possibilities are, but it's a point of interest and one I wanted to bring up yesterday. This has been on the exam a couple times, but usually not for anything particularly reasonable. They just usually at the end of some problem might say what is the capacitance of a sphere and have you kind of prove it. I think maybe 3 times in 50 years it might have come up. So this is not particularly common, but it is interesting. And because it's interesting, I thought it's worth pulling up. None of the other ones would behave in this way. So if you look at any of the other ones, you don't really get like a line of charge, doesn't really have the same kind of capacitance, and it'd have to be an infinitely long line for the other plate to be infinitely far away. And we don't really have infinitely long lines. Right? The farther away you get, the shorter that line looks. But a point charge can become a capacitor, and therefore any sphere can as well. That's a realistic experience. All right. I have something I would like you to look at, but is there any questions on the practice test that you took home that you would like me to go over? I thought they were very straightforward, but I would like to talk about them. Yes, sir.
2D.
2D.
It's determine the ratio of capacitance C with copper over C original in this lattice method.
Okay, so is this the one where you slide the thing of copper inside there?
Yep.
I thought I had a copy of it sitting on my desk. I thought I was going to be ready for you guys when you walked in, but then Mr. Leota came and he and I were chatting. And once we got chatting, I go, oh, there's one right here. But thank you. All right, so determine the ratio of the capacitance with the copper and the original. So let's see. We know the size of the copper, A. That's a good question. This is a good one. And this is one of those reasonable ones, meaning it's one of those ones that is not an unlikely possibility for an AP exam and shows up with pretty good regularity. They don't always put a piece of copper in there. Sometimes it's just some other conductor. But they'll put something in between the plates of the capacitor to try and make, to see if you understand how that works. So our first capacitance, they give us A. Yeah, it's just A over D, isn't it, or B? So you had to prove this. I think we've done this enough times where I don't have to go back through that, right? You had to find the new capacitance when you put a conducting bar in the middle there. So, or a conducting slab, it's probably what it said, a slab of copper. And they tell us that this is that big, right? Now, there's a couple ways to think about this. Since we're having a conversation about it, before I just go at the answer to the question, I think it's worthwhile showing you some possible things they can do. The first question I would have for you is, does it matter where the copper is? That's worth proving. Do you understand my meaning? Because, ultimately that should suggest that your capacitance works out to being that of a different parallel plate capacitor that looks like this. And is that what you get for the capacitance? Now, I don't know what you tried, but if it doesn't matter where you put that piece of copper, then that's a possibility, and that makes it pretty easy to figure out the capacitance, right? The question is that the same capacitance as if I move this and put this, say, here? There's a way to prove it. My question is, did you try to prove it? If you didn't, I think that's a worthy exercise. So let's try that, because I think it'll answer your question, okay? I'm going to put it not in the middle. I'm going to put it randomly somewhere between the plates. This is going to require us to do a little bit of math here, but I don't think it'll be much. Can we agree that no matter where I place it, because that area has no electric field, I have two choices on how I deal with the way I prove the capacitance. I could treat it like it's two capacitors in series. I could do it that way. Or I could go back a step and calculate the electric potential from here to here by doing the integral of the electric field. I don't care which way we do this. There's benefits and detriments to each. Which way would you like to do it? How about we do not A and B? Raise your hand if you want to see version 1 done. Version 1 would be to do the integration of the electric potential from the top plate all the way to the bottom plate. And who wants to do the combination of capacitance method? That's version 2. All right. Takes about the same amount of time. So let's do the combination of capacitance first. It's pretty easy. This plate and this plate, this capacitor, not capacitor. This one's going to have a gap that's going to have to be based on one of these two gaps that's here. So I need more space. So forgive me for doing this, but how about I make this, I'll just call that X. Is that okay? And then this space has to be B minus A plus X. I'm writing that very small, but doesn't that have to be true? Can you check my math on that? If I add all three of these together, I should get B. So B minus A plus X plus the size of A plus the size of X. Yeah, pretty clear. That gets me all of it. That equals B. So I think I'm pretty confident that those are my gaps and my relative gap sizes. So capacitor 1, or how we go, capacitor top, has got to be epsilon naught A over B minus A plus X. And capacitor bottom has to equal epsilon naught A over X. Does that make sense? So if I want the equivalent capacitance, that's going to be the inverse of 1 over C top plus 1 over C bottom. Sorry to bore you. That good? You guys see what I'm doing here? No. I'm doing this like very, very longhand. And I'm not trying to make you, to make this like kind of stupid obvious, but I get at the top B minus A plus X over epsilon naught A plus X over epsilon naught A, and then inverted. Do you see that the X's will just cancel out here? And I get B minus A. So this will be B minus A over epsilon naught A. And then that's just going to be exactly what we expected for the capacitance. Now, there is a massive problem with doing it this way, I think. It assumes that when we put the slab in there, we can break the capacitor up into two capacitors in series. Can you come up with a written or verbal explanation as to why that's okay to do it? Because if you can't, then you're just making an assumption that this is true. And we all know what the kind of trouble that gets me into with people who really want to know. So if that's not okay, this would prove it, because there's no way around doing this integral. But you guys seem to think that integral would be hard to do, and it's really not. That integral is super simple to do. And if you don't know why, well, let's think about it for a minute. Let's make this 0 and this B, and I'm going to integrate from this way to this way. Is that okay? The electric field between the plates still has to come from the charge on the plates. And based on what they say in the problem, did the charge on the plates change? Careful. I think they did. It won't matter in the long run, but I'm not trying to trick you. I'm trying to point out something. Be careful. If you look at the problem, they put the piece of copper in there while it's still connected to the electric potential. We just made it clear that when you do that, the capacitance changes, which means the charge had to change on those plates. It had to change. Right? So charge didn't stay the same because electric potential was there. Now that doesn't matter for the reason I'll explain in a minute, because we're trying to figure out what the new capacitance is. So after we do this calculation, we're going to walk over here and do Q over V to figure out what the capacitance is. So whatever the new charge on the capacitor is, it will cancel out. It has to. But I'm saying this to you because you don't always pay attention to the minute details. If this question D was actually a question about the charge on the plates after you put the copper in there, and you say it doesn't change, you will be wrong. Which is why I asked the question in the first place. Does everybody understand why I asked it now? Okay. It may be that I've seen your test. Possibly. Why I bring things up like this. So I want to point out that although it is true that the electric field is based on the charge, because the electric field between the plates we showed already is this. This will be the charge density on the plates, which is going to be Q over A. So the charge changes, but we'll eventually just have charge back in the problem, and they will cancel out. So it won't affect the change in capacitance, but it does change the charge. So this is our electric field, and that will be the electric field between any of the places that does not have metal. So when I look at my electric potential, I'm going to go with this from 0 to X. That's this section. And then from X to X plus A. And then when I do the electric potential, I have to integrate the electric field. But while I'm going through here, I start at this plate. There's an electric field here, right? And that's going to be sigma over epsilon. We know that from Gauss's law. There should be no electric field here. So during that section, my integral is going to have to be based on an electric field of 0. No change in potential. And then I pick that right back up here, and I continue until I get to the other plate. Thus, that's this electric potential. This will prove, if we get the right answer, this will prove that we can treat that space as if it's creating two capacitors in series. And I think you can see what's going to happen, right? This goes away completely. This is sigma over epsilon naught times x minus 0 plus sigma over epsilon naught times b minus x plus a. So I get, as my electric potential, sigma epsilon naught b minus a. And you can kind of see where it's going to go from there. Can you? I can finish it up if you need me to. But I think this was a worthy discussion. So are we good so far? Was this helpful? Did I give you a hint on what you should study? Mm-hmm. Okay. To see your answer now, to actually answer the question D, with copper, it's going to be, we're doing C with to C without, right? So this is going to be A epsilon naught over B minus A divided by A epsilon naught over B. This will be the ratio. And that's what it asked us for the ratio. So that's just going to be B over B minus A. And by the way, question C was probably different than you thought. Do you see why it has to be? So, you had to determine the electric field. The electric field changed the moment we put the copper in the plate. Yeah.
Did the electric field change because charge from the initial two plates was distributed onto the copper, or
No,
something like that?
but similar. The electric field changed because charges that were already in the copper redistributed. So the negative charges were pulled towards the positive charge of the capacitor plate, and positive charges were revealed at the other side of the piece of copper towards the negative side of the capacitor plate. So when we look at this, if the positive plate was here and the negative plate was here, the moment we put the copper in place, well, we polarized the copper and created negative signs here and positive signs here. Now, since the electric potential was the same, from here to here, the electric potential didn't change. Increasing potential, yeah. The electric potential didn't change between the plates. We basically made a dead zone in the middle of the plates where there was no electric field. So the electric field had to become more concentrated in the areas of the plates that did not have the copper, because we maintained the same electric potential. Basically, because the potential was the same, we had to concentrate it in a smaller volume inside the plates of the capacitor, so the electric field went up. If you looked at all of this, the capacitors increased because the copper is put there. It didn't decrease. Do you guys all see that? We effectively made the gap between the plates smaller. Yes, sir?
What would happen if you made the copper slab touch both the capacitors be zero?
Yeah. If you touch both sides, you'd make it so it's not a capacitor because there's no isolated plates. But you would get a different answer if this was not if instead you put a dielectric there versus a conductor. The conductor has zero electric field inside of it. But if you put a dielectric there, you still get an electric field inside the dielectric area. So if you did that, that would change the problem dramatically and make it a different question. It's not much harder. It would mean that here you would have an electric field, and it would not be based on epsilon naught, but on whatever the epsilon is there. You would treat it like three capacitors in series with two different dielectrics. Yeah.
Would you get the maximum capacitance by making the copper make the A as large as possible so that it barely touches?
Yeah. That's what you got right here, and that's what we've been seeing too, right? This is our capacitance. Capacitance increases as the gap between the plates decreases. So by making that copper piece bigger and bigger and bigger, that's all you're effectively doing is shutting down the distance between the plates.
So would that copper effectively act as a dielectric, but with an inverse relationship instead of a linear relationship?
I might get this wrong, so let me organize my vocabulary. Dielectrics have an electric field inside of them. So I don't think you could say dielectric, because it'd be a dielectric constant of zero, because there's no electric field, but that's really not effectively what's happening. So I don't want to say it like that. I don't think you can treat it like a dielectric. A dielectric, the charges are not free to flow around a dielectric either. There will be more things we'll talk about with conductors, but something else that happens to a conductor is every place on a conductor is raised to the same potential in an electric field. And that's not true in a dielectric. I think we've pretty well exhausted this question. But I think this is solid. And I think you can kind of see where I might be going on your test. All right. It's a good question, and this is turning into a total mess. But perhaps just consider it this way. Our original, when we're calculating capacitance, and we are doing step one for calculating capacitance, we are making an assumption that Q is some number we don't have to know. We're saying there is a charge that exists on the plates, and we are going backward. We're going from there saying this is the electric field. You were able to get the electric field between the plates immediately because you had access to what the capacitance was in the initial part of the problem, right? Once we knew this, we could figure out the charge on the plate because we had applied potential difference. So you can drop this in here and get an expression for the charge on the plate. And the electric field had to be this. Are you following so far, Jeremy? Because this is going to give you an obvious result, but I want to make sure you see it. When I drop, all of this in, I'm sorry. When I take that and drop it in here for the charge density, because charge density is Q over A. Bye. Have a good day.
Thank you.
You're welcome. And I drop all that in, I just get V over B. Right? Let's see. And this comes from the fact that we know the electric field's got to be a constant, and we applied an electric potential to our parallel plates, so we get this for the electric field. The electric potential didn't change, but the effective gap between the plates did. Right?
I think I got lost. But the charge density would be the same on the two plates.
No, it wouldn't. No, because this is our charge density under the current capacitor, right?
So
The new capacitor has more capacitance. So when I put the copper in there, it draws more charge to the plates.
So the amount of charge on the plates changed.
Yes. Because we stayed connected to the battery. We increased the capacitance while staying connected to the battery, draws more charge out of the plates. Because this ratio has to be preserved. This was a constant. This increased, so charge had to increase.
Okay.
If charge increased, then the electric field had to increase between the plates.
Okay, that makes sense.
I'll do this in small measure because I want to take us backwards. But I do this because I think it might not be a terrible thing to at least not leave hanging out there. You had this problem with why the electric field is 0 inside here, Jeremy. I've told you to use Gauss's law. It's a good reason to stop there, right? Because we know how Gauss's law works and why it tells us the electric field is 0, everything in there. It doesn't tell us something else that's important, which is that the electric potential is a constant everywhere in there. But you already know that if you wanted to calculate the electric potential, you could break this up into each piece, which would have its own similar, say, charge density. This brings up Oliver's conversation. That charge density, something like that. And we could figure out what this piece of charge is using that information. Perhaps we break each section of this sphere up into a small square, and we find all the different areas of the square. They would all contribute to an electric potential that'd be located at that point. It wouldn't be easy to do this calculation. You might be able to do it for a ring, and then maybe you could imagine it for a sphere. But you could calculate the electric potential and the electric field by doing a summation. The problem is, how do you do this summation? It's not as easy as other summations we've done, but it's a sphere. You know the equation for a sphere. And because you know the equation for a sphere, you could very likely, using that equation, find some relationship between every piece of the sphere, all the way around, so you have some integration variable. If it were me, I would look at perhaps the polar projection of a circle from a point. And not at the center. The center is too obvious. Make an offset point. You guys who are mathletes understand that there is a way to have a function with r and theta that would define a circle from any point inside the circle. Well, once you have that, you should be able to find the electric field from all those pieces. dq, I mean, I'm leaving some pieces out here. Let me be more clear. Or and solve it. I would try it two-dimensionally and work from there. Doing it to center is too easy because that's not going to prove enough to you. You would be able to just look at the symmetry and say, this is a waste of my time. Try doing it off center. If you do it for a circle, you will be, I think that will be enough to convince you. Now, I'm not saying you know how to do this. I'm suggesting that you might. And just to give you a starting point, find something for ds that could be in terms of dr and d theta, all the way around there. Now, for this, you'll need to know a little bit about polar notation. You should already have that. And you will need to find an equation for a circle projected from a point inside the circle. Now, I don't know that you know what that is, but it exists out there. You can find it. So you'll need one of those. So I don't know. I'm just giving you a place to start. If after this weekend, these 4 days, you try this and you get stuck, I will help you. If you don't try this, then what I'm saying is go to Gauss's law and stop being persistent in trying to prove it to yourself. But if you want to prove it to yourself, this is how you would do it. Be careful. This one, remember, is a vector. So you will have to find a vector relationship there. It might be easier to do this to show that it's constant no matter where the center is. Because if you know if it's constant everywhere, you can use this to ensure that if it's constant everywhere, its derivative must be 0. So just a couple thoughts on how you might do that.